Hi, everyone. Once again, it's a pleasure to introduce Rodrigo Mendes from the Universidade da Integração Internacional da Lusofonia Afro-Brasileira, in Lab, Redenção, Brazil. He finished his PhD at 2016 under supervision of Levi Brahe and Juan Nuno Palesteiros, and works on Lipschitz geometry of singularities. Today, he's going to give a talk entitled Metrically on Knotted Surface in R4. Please, Rodrigo, it's your turn.
Okay, Edson, thank you for introducing me. Thank you for the committee for inviting me. It's a big pleasure. Okay, let's start. In this work, we are interested in the study, in general, idea, the study of the topology and the metric type of the surface in R to the 4 that are algebraically parameterized. It means given as the image of a polynomial analytic map, so that this map is a topological embedded and has isolated singularities, they mention outside of the zero for some representative. And the first we make is it makes sense to speak about topology. In fact, is the link of the surface is a family of knots that are isotopic for epsilon is small enough. So the topology of surface is essentially identified of the topology of the knot given by the link. This is a kind of the conical structure for the maps. Well, a motivation for this study is the classical case of complex curves. If you have a plane complex curve and, given by the zero of the reducible analytic function, it's always a parameterized surface as in the definition above. It's because you have a Poiseuille expansion, then you have analytic parameterization, isolated singularity as well. And for the case, the topology, in fact, is completely characterized by it. You have the link of this surface is integrated top knots. It's included in the works of the Brown and Burrell and Zarinsky. I think it's good to comment, in fact, for these surface that are complex curve plane, the geometry of the outer geometry also completely characterized by its topology. This is strongly the beautiful result proved by Fan and Tessier and later for Alexandre Fernandes in 2003. So here the topology, the outer Lipschitz geometry, it means up to quasi-isometry is the same. But for the general case, you need study and then we start with this investigation. So let me give some definitions. The Lipschitz normal embedded or quasi-compact set means the following. We say that LNE means Lipschitz normal embedded of a subset is called Lipschitz normal embedded if the inner distance is the geodesic distance given by 2 points. You have the infimum of the length of the rectifiable path connecting SY, when it makes sense to speak about of this distance, for example, for kind of semi-algebraic or subanalytic sets, the distance well defined. When this distance is equivalent to the distance induced by the outer Euclidean distance, you say that set is LNE. So it's then, in order to start with the metric investigation, is a good point to check when the inner distance determines the outer distance if you have some subset embedded of the Euclidean space. other important definition of the tangent cone, the definition according to all context, is the set of the limit vectors based in zero. It means that you take, in this case, the limit of all the arcs on X given by the image of arcs from the plane. So if the set of these vectors, and the arc means a semi-algebraic map like this, then this it's called the tangent cone. It is this classical the tangent cone, in fact, and according with the Whitney tangent cone, in fact, you can speak about arcs you can prove this using the arc selection lemma, for example. And then definition 3 is a parameterized surface. We call this unknotted if the map is topologically equivalent to the map x, y, 0, 0. That's the most simple case of the surface when the link is just S1 given by the intersection of the plane. And its topological equivalence means equivalence up to topological change of coordinates in this parameterization. And you say that a parameterized surface is metrically knotted or metrically unknotted when it's knotted in LNE. As you have the two ingredients, you say the surface is metrically knotted. It's motivated the title of the talk. So let me justify this strong fact when you put some kind of metric irregularities, a linear property, included in the work of Alexandre Fernandez, is you can this strong fact. You have a complex arc, it's a parameterized surface, as if you have irreducible, and if this arc is LNE, then necessarily X is smooth, in fact. So, in other words, just for the question, in other words, there is no complex arc that are metrically knotted. From the complex axis, it's not possible to construct some topology different of the trivial topology if you consider the quasi-convex or Lipschitz normally embedded condition. So the question is, there are more generally algebraic parameterized surface that are metrically knotted. It means you have some topology of the not trivial topology, and together with the LNE condition. So this is the main question based on this investigation. And let me put some example in order to say that the fact that speak about parameterized, it's a good condition, this question in fact makes sense. Because for example, if you take a surface not necessarily parameterized, then the answer is yes. In fact, you can take the cone of any no trivial knot, smooth. You can take a smooth knot. If you take a cone, then you have a metrically knotted knot. So this question is completely solved if you have some general condition. But and speak about algebraic parameterized surface. So some steps. So there is a friendly ambient to start. If you put the parameterized surface, suppose the map has rank 1, the pulse of the derivative, you can present this parameterization in this way. The first coordinate is just x, and the other coordinates is 3 analytic functions. You can also take up to linear change of coordinate. The line x is centered in the line x. So you can also take the line x belong to the surface. In other words, this presentation can be seen as an unfolding of an analytic arc in the three-dimensional space. think about this arc, and then the surface is unfolding of this. Also, you can take the orders. You can order the orders with respect to the y variable. So, and for us, you say that this form, if we start, is called as a normal form. Okay. Okay, always hear me good? Yes. Mm-hmm. Okay. We make, if you take X as isolated singular surface, let's consider the following situations. One, if the two jet of the map is one of it is equivalent, means smooth equivalent, one of the two form quadrant forms, or up to change of coordinates only has this map and x, x, y, and two analytic functions of higher order. In both cases, by work of me and Ballesteros in 2016, you have the link is always trivial. Do not have knotted surface in this case. So in particular, if not, there is not knotted surface, there is not metrically knotted surface in that case. So you can consider a more natural condition. In fact, you can decompose these two jet and four types. This is two of these types. But if you can take more degenerate quadratic form, you can produce no trivial topology. For example, this surface, not this surface, the quadratic form is x, x, y, 0, 0, right? And the link of the surface is a trefoil knot. So you have some kind of topology happen, even to have put the condition of the rank 1 of the surface. So based in this question, I think now it makes sense to explain this main result of this talk. And the result is the following. If you take X, isolated singular surface, and suppose that the two jet, it's a smooth equivalent to this quadratic form, X, X, Y, 0, 0. So if X is Lipschitz normal embedded, if the inner and the outer distance are equivalent, then X is a metrically unknotted surface. So even in this case, if you take also the two ingredients, and then you do not have knotted surface in this case. In other words, you can see that to have some strong condition, as in the complex case, if you take complex arcs, remember, if you have a Lipschitz normal embedded, it's smooth and particularizing unknotted. Then these results show that for large kind of the surfaces, its property happen also. So I intend to speak in some details included of the proof of this theorem. Even if you have some particular situation, I think that some kind of a strategy in this proof can be generalized for the amplify this result. So the general strategy is the first is take in order to encode the knot type, we take the projection for the R3. If this projection is generic, then it means the link has just transversal double point. These double points given a classical knot diagram of the link. So it's the first natural step. If you can check what happened with the topology, with the knot, you can see, you can check the the diagram, and you have a partial information of the node. And also you consider the projection for the plane in the generic way. This means that the kernel of the projection is not intersect the tangent cone just in the origin. In other words, the tangent cone has a good position in this projection. And we take projection in this way, then a part of the topology and the metric behavior can be detected by the ramification locus. It's classic in some sense strategy. And in all particular case, let me speak how to can extract the information on the metric and topology point of view. In metric, specifically talking. The proposition 1 is the following. If you take in general a subanalytic surface, suppose the surface is flat, because for rank 1 you can show that all surface is flat. That means the tangent cone is plane. Then this projection is a finite map and a Ham-Phi cover, but inside of each triangle, this triangle means the region bounded by the two arcs contained of the discriminant of this projection. Okay, so in the real case, it's more, it's a little more degenerate. You have not exactly a Ham-Phi cover, but a Ham-Phi cover for each triangle. It means that for each triangle bounded for arcs on the discriminant, the number of the pre-images of the multiplicity is the same, but it can change. And then proposition 2, as X as above is the flat surface and Lipschitz normal embedding, then outside of a null density subgerm, the multiplicity is equal to 1. The null density means if you can take outside triangles also in the plane, as triangles that have bounded for tangent arcs. It means that the volume, the behavior of the volume, it's more collapse more fast than the volume of the two-dimensional ball. I think then if you put L in E, then we can speak about multiplicity 1 outside of this set. And in other words, it says that no trivial topology, or if you can check the trivial, no trivial node type, this happens exactly on these thin triangles. Outside in the large part of the link, you do not have topology. Exactly on the zones when the possible the topology and the cosines happen. It's in some sense, in fact, exactly is a kind of a very particular case of the thin decomposition. It means that in the geometric point of view that's proved by Hibrahi, Ampshon, and Walter Neumann, that show that and for kind of analytic surface in the complex case, you have a thin part and the thick part, and the most part of the topology and the Lipschitz geometry release on the thin part. Okay. So you have this scenario for this kind of projection, and okay, and all the truth for this proof is the LNE arc criterion. Is the good tool, in my opinion, because as usual, it's not good to check some property from the definition. It can be hard or not possible. So these results, let me list the definitions and then I speak about this criteria specifically. The definition 5, an arc, I speak it before, but again, that arc is the image of a continuum map germ like this. the definition X, if you take f a function, and X embedded in some Euclidean space, and an arc. Suppose this arc is contained in X. Then you can consider, when it's possible, the order of f along of this arc. Then this number is given by the order of the function composed by this arc. This is possible, for example, if you speak f about some nice structure. F is analytic or subanalytic, this arc subanalytic, or more generally, if this structure is polynomially bounded, then this exponent is just the exponent of this function. It's a series for fractional exponents. Okay. The next definition, take the two analytic arcs and some subset, parameterize this uniformly in some way, and you can define two numbers. The outer tangents order is the tangents order of these arcs, is just to take the order of the distance function between these arcs. And when it's possible, you can speak also the inner tangents order. It's the tangents order of in a similar way, but now you replace the outer distance for the inner distance. So in a large kind of cases, when, for example, X is the same algebraic, these numbers is well defined. For algebraic sets, for analytic sets, for subanalytic sets, you can speak about of these exponents. So one result for me and Bibray in 2018 is if you have a same algebraic germ, then any condition means that these two exponents are the same for any pair of arcs. This means the order of the outer distance is equal to order in the inner distance. So this one direction is immediately from the definition. The other direction can be more useful in order to use effectively this criteria. Okay, let's continue. And from this, we can define the following objects back into the all setup. You have a parameterized surface. You suppose the surface is flat. Suppose you have a generic projection, and suppose that the discriminant is not just the zero. Then you can define the width of X respect to some triangle in the plane of just the contact on these boundary arcs of this triangle, when these arcs are bounded are content of the discriminant of the projection. It's some try to mimic of the width and of the some Euclidean geometric object, and use the projection in the plane. Then you can estimate how the width of the surface and the structure of the triangle. And you can define the height of X restrict some arc of the minimum of the contacts of the pair of the prime measure of arcs. When suppose the map is finite, it has some regions of the multiplicity greater than 1, for example. I think it's good to draw some picture. Suppose you have a surface, and then to have the link and in black, and this arcs in blue is the discriminant set, and they have some prime measures, and then the height is the infimum of contact, meaning the larger distance on the arcs of the prime measure of discovery. So one criterion is basically consequence of the linear criterion. If X is Lipschitz normally embedded, then this width is necessarily greater and equal in the height. For all arc, I put in aspects in the middle of the triangle. It means if you take arc such that the contact on the boundary is the same. This criteria not work if the arc is very high tangents on some arcs of the discriminant. It's like in the picture, the arc gamma is the middle is not exactly the middle, it's in the contact point of view, of course. So then you have this criterion and use this criterion to prove the main result. Remember, the main result is some condition of the parameterization. You do not have no trivial ones. Okay, let's back for the proof of the main theorem. Maybe you can remind this. Isolated singular and surface, and the true jet is smooth equivalent is quadratic form. Then Lipschitz normal embedding implies you have not unknotted surface. Okay, let's back for the equations, and you consider the first case, and if you have the map that parameterizes the surface in the with the dead quadratic form, you can write in this way: x, x, y, and have term of high order, and the two analytic functions belong to some maximal ideal of the exponent tree. Yeah. And these two functions belong to the ideal, and assume that this order are given in this way. This order 2k plus 1 lengths the order or the function f3 and f4. One result that I mentioned before is for the case of the surface given by this unfolding of analytic arc, the tangent cone is always the plane, is the flat. This in general is some of the plane, but if you can take a normal form, then you have exactly the plane with these coordinates. So the good point is the projection you can parameterize basically of a map of the plane to the plane. You have this map that given the behavior of the projection of the tangent cone. You can take the singular locus of these projections, is this algebraic set, so this analytic set is a graph of x, it's just compute the partial derivatives. And then you can parameterize, it's after to parameterize the singular locus and you compose with the parameterization, then you have the exactly parameterization of the bundle of the discriminant. So you have this picture, you have some region bounded for a parabola in the plane, and the image of this projection is in the cusp bounded of these exponents. And in this way, all line, when you take a normal form, is exactly the arc that you need. It's having in the middle on the contact of point of view. In fact, he is exactly the middle. And then you have that cone, the width of the surface is this, has this number 1 plus 1 divided by 2k. And in fact, these arcs are tangent, you have contact. And for estimate the height number, I take some more pictures. You have some situations that take arc and take prime images, then have the situation 1 on basically the distance of the arcs has same contact, but can have in the second picture the arcs has high tangents. So the height of the arcs from the tangent cone is not exactly the same contact. And then you can, in the geometric point of view, you can arcs on the same side of the other side, respect the tangent cone. So when get by triangle inequality, essentially, that the height is greater than the contact of the x from the tangent cone, restrict the gamma. This multiply this notation, it means that you just compute the contact of these arcs on its image. So some measure the contact of the surface from the plane. This inequality is good for this particular proof because in the parameterized case, it allows just it's more easy to compute this contact. It's just take the minimum of the order of arcs composed by the last two coordinates. It means you have gamma on the floor, use all parameterization, and this arc is image of the map F. But sorry, there's some confusion of notation. This gamma is not exactly the gamma in the floor. It's the gamma in the per-image. Okay, it is parameterized by F. This picture, I think, is explained better. You have this gamma is in the per-image of the line. So this distance, this contact is given by the minimum of these arcs. After possible, you reparameterize these arcs to take real contact of this, which space this arc. Okay, and then in red, this arc underlined gamma can be computed from the parameterization. Is exactly it's the zero set of the two coordinates, because to project on the line, you have necessarily the second coordinate is equal to 0, right? It means that the projection is exactly on the line in the x-axis. Okay, so considering that the two last functions belong this ideal, one has the good inequalities directly from the computation. The order of the, suppose without loss of generality, the minimum is realized by the Q, for example. So the order is just replaced on these monomials, and then you have this inequality. It's 2 plus 1 divided by 2, 4 is greater than the width. If suppose the ordering given by the second monomial, if you have the order monomial, and then you have this inequality, it's almost it's work also. And then for considering the last exponent, you have also this order. Remember that you have a normal form. The Q, it means the order of the Q with respect to the Y variable. So in the three cases possible, the ordering is greater than width. Then it means that height of the surface is greater than the width of the surface. It means that the surface it's not possible the surface is Lipschitz normal embedded. Sum up, it means that Knot surface cannot happen from this normal form x, xy plus f2, f3, f4. If the order is ordered in this way, it cannot be metrically knotted. Remember that you can take some knotted knot, for example, is this exactly like this example, right? The order of is 3, 4, 5, and then it's not Lipschitz normal embedded surface. Okay. So And you consider to check if you have a metrically knot surface, this other possible case which take this order. This orders, suppose now this order of the parameterization respect y is not given by the coordinate that contain the quadratic form. Suppose the without loss of generality is the function in the coordinate 3 given this order. And the point is the order is always odd because one implicit fact on these parametrizations is, let's speak, the tangent cone is always plane. Oh, sorry. Okay, yes. But in general, can be happen. This order is odd. The tangent cone is whole the plane, but the order is even. So the tangent cone can be a half plane. But since you have the Lipschitz embedded hypothesis, so this exponent is necessarily odd. And remember, these two first coordinates parameterize this projection of the surface on the tangent cone. So from this parameterization, you can estimate or compute the double point set. To remember the first strategy to check the topology of the knot, you can project generically in the three-dimensional space. Then if you project in this way, x, f3 and f2, the double point is friendly also. You have this given by these two equations, you detect the double point set. And the first equation, I take some, not a lot of equations in one time. But the first equation is given by just replace this equation, the second coordinate, and the other coordinate, you have this equation. So the double point set necessarily satisfies the two equations. Writing the f, this function, right in this way. So if you speak about the initial term of this equation, consider these sets, the last part is a homogeneous polynomial, then you can, in the first equation, you can explicit in terms of x, write this function, and then we replace in the second equation. Just directly computation, how we solve some pair of equations. When we replace, you have this equation, but if you have the condition of order, the initial part is this equation. Okay? It is homogeneous polynomials, the zero homogeneous polynomial. But it is in the real case, this polynomial has no solutions. There's no real solutions for this polynomial. So this equation don't have real solutions different of the 0, 0, 0. It means the double point set is trivial. So the projection does not have double point. So this knot is trivial. So in the all case, you have trivial knot. So if you ask about the metrically knotted surface, you need to investigate more degenerated cases. Okay, this is my plan for today. Thank you, everyone.